Hello everyone, and thank you, Axel, for the intro. So for the last 10 odd years, I've been working in robotics, starting originally as a researcher at the University of Sheffield. And then for 5 years now, been working in industry on a company that I founded, working on a software product that is looking to improve the programmability of robots and also to make software systems more modular within robotics and importantly cross-compatible across different robot platforms. So when asked to talk about scaling autonomy through software and systems and robotics with a bit of a focus on neuromorphic, so my first response was, I haven't really done much neuromorphic in my research, but I have been exposed to it through the Human Brain Project, which I was part of when I was part of the University of Sheffield. But I thought I'd start first with a video of sort of one of the first projects that I was involved with here at the University of Sheffield, a project called Wizawit, What You Say is What You Do. And that was led by Professor Tony Prescott here in Sheffield and Professor Dr. Paul Verschoor at the University of Fabra, both of which sort of are currently running the workshop next door. But the aim of the project was to turn a theoretical cognitive architecture into reality and apply that to a real robot and explore those challenges. So this was the result of the 4-year project implementing quasi-modular systems that brought different capabilities to the robot. And so to set the stage, deep learning was very much still in its infancy at this point. Results at that.
Is there a video?
Oh yes, video's coming up.
Oh, okay, sorry.
No worries. So the results primarily at this point with the neural nets have been found with convolutional neural networks. So we had a bit of that with object recognition, but everything else consisted of handcrafted algorithms that leverage different machine learning techniques that were brought together and integrated for this project. So I'm just going to run this video. It's a bit of a long video, but I'll let it run through. That's good. Oh, did you convert this to a PowerPoint? Right. Okay, so that takes us there.
Have we met before? Yes, I remember. Nice to see you, son. Watch, please. I will move part of my body. So, how do you call this part of my body? This is your head. I understood this is your hand. Nice. I know that I have a hand.
So you can see in the background all sorts of different systems running with their own displays.
Let me show you on the screen. Look, because our hands look the same, I know this is your hand. I know how to move my hand, but how does it feel when I touch something? Can you touch my hand when I move it, please? Thank you. Now I know when I am touching an object with my hand. What have you learned from your arm? Please look at the screen. See how my arms look the same. What's the duck? I don't know which of these objects is a duck. Can you show me the duck, son? the octopus. I've understood this is the octopus. I get it. This is an octopus. Give me the blue cube. There was only one object which I didn't know. Now I know the blue cube. I will push the blue cube to the front. I will move the object to the shared area. Can you please pull the blue cube towards you? Well done. Now you have the blue cube. I will push it down to the front. I will push it down to the front. And move the object to the shared area. Can you please pull it up towards you? Well done. Now you can go. How do you call this action? You did a push action on the duck. What did we have the other day? Sure. What do you want to know? What happened first? What first? First I want the octopus. Another head. Okay. Then I reason. What happened next? What happened next? Okay. Then I say, give me the octopus, please tell me. What else? Then I reason. What happened finally? Well, finally to leave the octopus. What happened then? Well then Toby gave octopus to me. What happened next? Well then I reason. What happened finally? Well finally to leave the octopus. Why did Toby have the octopus? Why? Toby asked the octopus because I say give me the octopus, please Toby do. Why is that? I say give me the octopus, please Toby because I reason.
Right, so as you can see, quite a capable, although painful, interaction with the robot, as it's quite slow, it is not as accurate. then comparing it with something that's a bit more recent. So that was 2017. Now going fast forwarding.
So, in terms of salary, you were thinking.
We've indeed set salary expectations from the start.
There we go.
Hey, figure one, what do you see right now?
I see a red apple on a plate in the center of the table, a drying rack with cups and a plate, and you standing nearby with your hand on the table.
Great, can I have something to eat?
Sure thing.
Great. Can you explain why you did what you just did while you pick up this trash?
On it. So I gave you the apple because it's the only edible item I could provide you with from the table.
Great. So, based on the scene right now, where do you think the dishes in front of you go next?
The dishes on the table, like that plate and cup, are likely to go into the drying rack next.
Great. Can you put them there?
Of course.
All right, so how do you think you did?
I think I did pretty well. The apple found its new owner, the trash is gone, and the tableware is right where it belongs.
I agree. Thanks, figure one.
You're welcome. If there's anything else you need help with, just let me know.
So, after 7 years of progress, here we go. So, after 7 years, one of the most impressive demos that I've seen in recent times, and we've got so much more advanced level of capability, smoother motion, smoother interaction, more natural language interaction, and much better perception. But this time, however, all the functionality is integrated into probably a single black box, a vision language action model, running on multiple GPUs. And so there's been incredible progress on the side of improving the capabilities of robots. But along the way, we've also lost a bit of the introspection, the capability to look at the different pieces of the system and the different modules and be able to address what they are doing. And that directly impacts then the scalability of these software systems. So if we were to compare the two different points in time, we can see from an architecture perspective, WYSIWYG had modular, very loosely coupled systems where you could essentially interchange different models. Whereas if you're using a VLA model, you have an end-to-end pixel to joint position control. From an integration layer perspective, you had very extensive work done on integration by multiple teams. And now you've got a predefined integration defined by the model that you've trained. But you also had, in terms of sensor adaptability, a high level of sensor adaptability that you could add sensors, you could plug in different sensors, and merge them into the rest of the system. Whereas with VLA models, it's very brittle. You've got a fixed number of sensors that you're using and of a fixed input size. And finally, we went from a heavy CPU load, in the case of the Arco, to a heavy GPU load. So compute-wise, we're still even more of a power draw. So the question is, sort of, it's not that I'm saying anything against like PLAs or deep models, but I believe they have their place in a more modular system architecture and should be used as tools alongside other approaches. And so for the last 2 years, there's been over $7 billion invested into robots for household and warehouse applications. And there have been leaps and bounds on AI capabilities and accuracy. But in terms of unsupervised autonomy in the real world, we are still behind on actually being able to deliver that. Because the models that we have that are somewhat capable of delivering that can't run on the robot itself. You have a big discrepancy between the best onboard devices in terms of both memory and compute power. And so you have this discrepancy in terms of being able to actually deploy these models. So in order to circumvent that, first thing you do from a software perspective is split the compute. You have some modules that are running on board the robot, and you have modules that are running off-board, potentially even in the cloud. So that allows you to work with the existing compute on the robot, applying that towards more safety critical systems like motion safety, feedback control, and in the meantime, off-board, all the heavy compute, especially around perception, around decision making, and put all of that into the cloud. And that brings a couple of pros. You've got less compute power draw on the robot, meaning you've got longer battery life, unrestricted compute in terms of being able to prototype your perception and your decision-making systems. But you also have a number of pretty serious cons, both in terms of system architecture, but also in terms of actual commercial deployment. So you've got high failure probability when it comes to that network connection. You have non-deterministic latency, which based on the control systems that you might be using, really interferes with your capability to process the information. And a lot of people have security and privacy concerns. If you're streaming all of the video, all of the audio, and other highly sensitive information to the cloud, to process it in order for the robot to be able to make a decision and act, then a lot of companies actually don't want that. And finally, of course, you've got then the cost of connectivity. Having a reliable connection means you're engineering an environment for that robot where you have constant communication throughout. But this is a model that allows us to keep pushing forwards in terms of what's possible today. And for the last 5 years at Bow, what we've been doing is standardizing the data exchange between the onboard and the offboard computing in order to provide easy-to-use SDKs and easy-to-use communication that will allow you to continue building modular systems that will provide the capabilities that we're looking for. So in terms of a common language to scale software, we'll talk about scaling the systems side later on. But in essence, when you boil down a robot, it's an input and output device. You don't need anything else but to know, I just want the information for this specific modality, and I want to set an output, which is either an action, something that the robot says, or something that the robot is conveying to the user. So in terms of scaling the software, if you boil down a robot to its inputs and outputs and structure a language around that, that means that you can now scale the applications created on top of that middleware and be able to create a single application that runs on multiple different robots, regardless of their sensory capability, regardless of their kinematic structure as well. And so with this approach, it doesn't matter whether it's a humanoid, a wheeled, or a drone robot. And so get vision, gives you, for example, all of the visual sensory information with all the metadata needed to make sense of that sensory information. Unlike a case with middleware like ROS, where you would need to know things like data type, you'd need to know its position on the robot body from a different source of information. And so we've combined that all together so that it really simplifies the control of the robot. And so the end result is that the data is completely decoupled from how it's sampled, making it possible to create applications that can scale across different types of robots. We've got a short video here.
Fast delivery, thrilling entertainment. It's on Prime for $8.99 a month.
On Booking.com, it's easy to go for holidays. To a holiday home. Book with free flexible cancellation. Booking.com. Booking.yeah.
Hello everyone, my name is Eleanor and
So here we have a robot arm from Elephant Robotics, and I'm moving the handles in Insight to update the inverse kinematics position objectives. And you can see that this robot is responding quickly to the motor commands. But I was kind of interested when we did this demo that you can see a bit of a lag on the screen for the robot model. Now that actually reflects the limitations of this particular robot in terms of the rate at which it's able to sample the joints and generate sensor updates for the computer to read. So it's really important to be able to see the actual capabilities of the robot, not just the simulated capabilities, and Insight's very useful. Insight can also be used for teleoperation. So here we can see the Miro robot from Consequential Robotics, the little dog there on the table, which is providing a live video stream, and which you can see in the top right of the Insight panel, and it's responding to inverse kinematics controlled head movements as a simple example. You can see how this can be, Insight can be used then to monitor the sensors like the visual feed of a robot that might be operating remotely. And Insight can of course be used for much more sophisticated applications like monitoring and inspection when it's deployed on our more advanced robot hardware platforms like the SID1 and Quadruped from our partner Motion Robotics. So here we're calling predefined action patterns for locomotion, and we're able to use Insight to monitor the state of robots having traveled over great distances and go offline. So we're really excited to bring you this kind of sneak preview of Insight, which we think is the start of something quite special for the future of robotics. Insight allows you to deploy the Bow SDK on multiple robots, which is what the Bow SDK is in part designed for, and to interact intuitively with the sensors and the motors of your robot, irrespective of the type of robot that it is, whether it's an arm, a wheeled robot, a quadruped, a humanoid. And as a quick demo, what we're showing you here is how easy it is to use Insight and the Bow SDK to manage a small fleet of robots and to visualize their states in 3D and control their movements in real time. So the operator, Daniel here, is running 3 instances of Insight, each one connected to a different robot in one of our offices here, and he's able to provide the same set of instructions through dragging handles around in Insight and this robo-agnostic layer of the SDK, and the 3 different robots are then in real time carrying out those actions, and Daniel is able to monitor what's going on and inspect exactly what's happening.
So that is just a brief sort of overview in terms of being able to control different robots with the same software through the same commands. And then the question starts to become, where is, in terms of deploying autonomous systems, where is the division between what goes on board and what goes off board? And so status quo today is a lot of the time, if what we're doing is we are putting anything above perception off board, and we're simply dealing with the communication to take that information back to the cloud, process it there, reach a decision, and then send it back to the robot. But the ideal would be if you could run perception on board, but without the associated power cost, while keeping the robot running for an extended period of time with its existing battery capacity. And that is exceptionally hard because when it comes to perception, those are often one of the more computationally expensive parts of the cognitive architecture that we're running. So that starts to then bring into the picture neuromorphic computing. So with event-driven neuromorphic sensing and computing, it could make a big difference. So rather than running a synchronous computation on every frame, regardless if there has been any information change within the scene, you could be instead, of course, running with asynchronous events in a way that actually the robot could even respond faster than the equivalent with a traditional sensor. And of course, the energy saving actually scales with the complexity of the data that you're processing. So if it were possible to run high fidelity perception locally on the robot without the traditional power draw, that would really mitigate a lot of the cost of the split compute approach, because it would mean that you could have very simple decision making happening on board the robot, given that it has all the perception information, and then use that to get into a position, if you're a tricky one, to go back to off-board decision making, which is for more complex, more longer horizon routines. And of course, if you're only transmitting percepts from the robot to the cloud, then that also avoids any security or privacy issues around the raw video and the raw sensory data. So, and of course, that also reduces the bandwidth required. So, multiple different advantages available. However, if I look at neuromorphic computing and sensing from a commercial perspective, what I see is that there are a couple of important technical hurdles that the neuromorphic community would need to overcome in order to initially cross the chasm. And so the first one I've noticed is that dev tools are available, but the interoperability of those tools is very limited. The hardware itself is quite niche still and relatively expensive compared to commodity sensors. And you also have still a very limited number of use cases where neuromorphic sensing has been proven and demonstrated in real-world applications. So that's on the technical side, but actually there is a more serious question on the market side. Today, everyone's default is NVIDIA. CUDA, TensorRT, Jetson is a very vertically integrated ecosystem that is currently pretty much dominating the robotics side in terms of being able to deploy these systems. And so the challenge here for neuromorphic computing is that in order to replace the incumbent, it has to be 10x or even 100x better than existing solutions, not just from a performance perspective, but also from the ease of use from a developer perspective. And that, I believe, is a significant challenge that neuromorphic computing has, even with all of the advantages that it can provide towards autonomy for robotic systems. That's it for me.
Your time.
Perfect.
Thank you so much for amazing talk. Daniel will be with us for a panel discussion as well. So I think it's time for a coffee break. So we can have further discussion during the panel session. And during the coffee break, we also have few quick interactive demos with event cameras if you want to try them. Kind of music to create with sensing very small particles.